Section 12.8, liquid crystals. Okay, you know what solids are. Solids are characterized by order. And you know what liquids are. They're characterized by kind of a random ordering of the molecules. The attraction is not so strong, and so they can slip and slide past each other. Okay, what has been discovered is that there are some intermediate forms. Okay, there's phase where some liquids show a limited amount of ordering. So it's kind of a halfway between solid and liquid. It's not that it's partially melted. It's all the way melted as a liquid, but at certain temperatures, this liquid has some characteristics that a solid would have. Okay, and that's what is so fascinating about it, and makes it interesting to study. Okay, so this one, this picture here is one of the first materials that they isolated that has this property. It melts at 145 degrees. Okay, so it melts from solid to liquid. So it is a liquid, but between 145 and 179, you get a kind of a milky characteristic. That's on the right. So it is milky and liquid crystalline. And then at 179, the milky liquid suddenly clears. Okay, so it flows like a liquid, but possesses some order like a solid. And so just because of how interesting that is, you can, hey, market that. Let's make some money on that. All right, so let's look at some of the types. These are some of the types of the phases. Okay, so liquid crystal molecules are usually long and rod-late. So in normal liquid phases, they're random. That would be like on the left. They're randomly oriented. So they've got the molecules of this crystal are long, almost like fibers. So they can random, and then they exhibit three types of liquid crystalline phases, depending upon how it's ordered. Okay, so the first one, you have pneumatic liquid crystalline. That is on the left. And I'll go through this more in detail in just a second, wherever they're all lined up. Then smetic, okay, they're ordered along the long axis and in one other direction. Okay, so usually on one axis onto the other. And then you have the cholesteric liquid crystalline phase, which is very, very orderly. All right, so sometimes crystals can have different phases based upon different temperatures or different amounts of electricity passing through them. So you can overlap crystals, and a lot of times that makes it really useful. Okay, so here's the first one, pneumatic. So pneumatic liquid crystals, molecules are only ordered in one dimension. Okay, so one axis, that's easy. Okay, the next one is smectic. Smectic crystals are ordered in two dimensions along the axis and in layers. So it's not just random in one area, but it's almost like rank and file, to where they're lined up and they're lined up almost in two dimensions. They're all long ways in one direction, but they're in rows within the material. That's called smectic. Okay, and then cholesterol liquid crystals, pneumatic-like crystals, are layered at angles to each other. All right, so you can have one and then have another angle and another angle. Now, of course, you're doing that. That's not necessarily natural. You're making one layer followed by another layer, and you're putting them at different things. And of course, the darker overlap you can have, the darker that material will look when you see it. Otherwise, it's going to look transparent. So you can make something appear that wasn't there. Okay, that wasn't there a moment ago. So you can do this with light, you can do this with heat, you can do this with electricity. So these crystals exhibit color changes with changes in temperature. Okay, I have a piece of plastic that I can put in the microwave, and when I pull it out, I can see the wavelengths of the microwave that was hitting that crystal. So I can actually measure the wavelength along that wave pattern of it.